Hello students, welcome to experiencetutor.com. Today we'll go through IIT Mathematics Complex Number Part 2.
Let us start with the welcome message. Dear students, welcome to our channel experiencetutor.com. In this channel, we will teach physics, chemistry, mathematics and biology for the students of class 10th, 11th and 12th and those who are appearing for the school board examinations and entrance examinations like IIT, NEET and all state level engineering and medical examinations. This course is organized according to different topics for each subjects. Therefore, it contains separate video for each and individual topics. Hence, it covers complete syllabus for CBSE, ICSE, ISC and all the state board examinations and engineering and medical examinations. You can also find the relevant topics for foreign school examinations like SAT, IGCSE, IB, etc. Enjoy your learning. Thank you.
Today we'll go through different forms of complex numbers. So, a complex number may have three different forms. First is Cartesian form. First is Cartesian form. So let us see what is this form actually. Uh, if x is equal to if z is equal to x plus iy, if z is equal to x plus iy, where x and y are real number, is known as Cartesian form. We have already discussed about the Cartesian form in our first video. Now, what are the uses of Cartesian form? This form is generally used to locate any complex number in Argand plane. Secondly, it is used to find the locus of a complex number. The next form is polar form. Let us see what is this form. In polar form, we write r and theta. So it the complex number z can be represented as r cos theta plus I sin theta. So here r theta is known as polar form of complex number. Where r is equal to modulus of z r is equal to modulus of z and theta is equal to argument of z. In the given triangle, we have x is equal to x is equal to r cos theta and y is equal to r sin theta. Since z is equal to x plus iy, therefore we can write the same equation as r by putting the value of x and y as r cos theta plus I sin theta. is equal to R CIS theta. Instead of cos theta plus I sin theta, we have written CIS theta, which can be written as e to the power I theta. Uses of this form. First, when the power of complex number is very high, this form is used. Second, in problems of maxima minima, this is used. And third, to find out the nth root of unity, it is used. Now, Euler's form. The third form is Euler's form. So, Euler form. Z is equal to R e to the power I theta. Z is equal to R e to the power I theta is known as Euler form, where R is equal to modulus of Z. So we can write R as modulus of Z, and theta is equal to argument of Z. Theta is equal to argument of Z. Euler form can be converted to polar form by using e to the power I theta is equal to cos theta plus I sin theta. So therefore we can write Z is equal to R theta I theta is equal to R cos theta plus I sin theta. So all the three forms, these are all the three forms. Here let us solve a problem. If z is equal to 1 plus root 3I, represent this in polar form. So we can write z is equal to 1 plus root 3I root 3I modulus of z is equal to 2. Argument of z is equal to pi by 3. Therefore, polar form will be equal to cos 2 is r, cos theta is pi by 3 plus I sin pi by 3. Our next question is multiply z1 is equal to 1 plus I and z2 is equal to root 3 plus I using Euler form. So in this case we'll write z1 is equal to root 2 cos pi by 4 plus I sin pi by 4 is equal to e to the power is equal to root 2, sorry, root 2, this is root 2, okay, root 2 e to the power I pi by 4, I theta, so theta is pi by 4, therefore I pi by 4. Z2 we can write as 2 cos pi by 6 plus I sin pi by 6, which is equal to 2 e to the power I 5 pi by 12, 5 pi by 12. E to the power pi by 6, 2 e to the power I pi by 6, because theta is pi by 6 here. Therefore, if we multiply Z1 and Z2, we'll get 2 root 2 e to the power I common pi by 4 plus pi by 6. Therefore, 2 root 2 e to the power I 5 pi by 12. Now, it can be written as 2 root 2 root 3 minus 1 bracket closed upon 2 root 2 plus I root 3 root 3 plus 1 2 root 2 bracket big bracket, which can again be written as root 3 minus 1 plus I root 3 plus 1. And this is the answer. Now we'll study about algebra of complex numbers. First, equality of two complex numbers. Two given complex number z1 is equal to x1 plus I y1 and z2 is equal to x2 plus I y2 are said to be equal if respective real and imaginary parts are equal. So if z1 is equal to x1 plus I y1 and z2 is equal to z x2 plus I y2, then and if we say that z1 is equal to z2, then x1 should be equal to x2 and y1 will be equal to y2. Now we have a question. Find the value of x and y if 2x plus 3y I is equal to 2x plus 12I, where x and y are real numbers. So in this case, two complex numbers are equal. Therefore, the real parts and imaginary parts are equal. Therefore, if we equate the real and imaginary parts separately, then we will get as 2x is equal to 2. Therefore, x will be equal to 1. If we equate the imaginary part, then 3y is equal to 12. Therefore, y will be equal to 12 upon 3, which is equal to 4. If we have two complex number as z1 is equal to x1 plus I y1 and z2 is equal to x2 plus I y2, then if we want to add z1 plus z2, we will get x1 plus x2 plus I I y1 plus y2. In polar form, we can write z1 plus z2 as z1 plus z2 as r1 cos theta 1 plus I sin theta 1 plus r2 cos theta 2 plus I sin theta 2, then we can write it as r1 cos theta 1 plus r2 cos theta 2 plus I sin I r1 sin theta 1 theta 1 plus r2 sin theta 2. Now let us discuss about the properties of complex numbers. So first is closure law. According to this law, if two complex numbers are added, the result will also be a complex number. So z will be a complex number if we add two complex number z1 and z2. Now commutative law. According to commutative law, uh, if z1 and z2 are two complex number, then z1 plus z2 will be equal to z plus z1. Third comes the associative law. According to associative law, if z1 and z2 are two complex number, then z1 plus z2 is equal to Z1 plus Z2 bracket Z2 plus Z3. Now additive inverse. Additive identity first. For every complex number x plus iy, there exists a complex number 0 plus i0 such that x plus iy plus 0 plus i0 is equal to x plus 0 plus I plus I y plus 0 is equal to x plus iy. This is additive identity. Here 0 plus I0 denoted as 0 called additive identity. So we can write it as for every complex number x plus iy we have 0 plus I0 is 0, which is called additive identity. Now the fifth one, additive inverse. For every complex number z is equal to a plus ib, we have a complex number minus a plus I bracket minus b denoted as minus z called additive inverse or negative of z. So if we have z is equal to a plus I b, then we can say that additive inverse of z is, or we can say minus z, which is additive inverse, is minus a minus minus b. This is also known as negative of z. Geometric representation.
And this is the end of this topic. If you like this video, please subscribe our channel and give us a like sign. Please click on the bell icon so that you get automatic notification when a new video is uploaded by us. Thank you for watching our channel.